In this part of the lecture, we briefly discuss the algebraic form or Cartesian form of the complex numbers. Cartesian form of the complex numbers comes from the fact that algebraically complex numbers are just real numbers which are combined with this extra element, the imaginary unit. It's the number which in square delivers -1 or just the root of -1. So informally speaking, you can actually, it's more or less formal, you can just understand the complex numbers as the real numbers plus another set of real numbers times scaled by imaginary unit. Or this line actually, you understand this line in the following proper terms. Any complex number z admits the representation like this, a plus bi, where each of the a and b are real numbers and I is the imaginary unit. This representation, that's the one which is called algebraic form or Cartesian form of a complex number. The elements a and b, they have a name. For instance, a is called the real part of a complex number z, and there is an abbreviation for this, z, and b is the imaginary part of the complex number z, and normally it's denoted by im_z. Right. When you do arithmetic with complex numbers, so when you do arithmetic operations with complex numbers, let's just look at that. So I'm talking about the addition, subtraction, multiplication, or division. So addition, subtraction, multiplication, and division. There are a few ways you can do that. But if you have complex numbers which are given in the algebraic form, like this, z is a plus bi, and w is c plus di, where a, b, c, d are real numbers, so a, for instance, and b are real and imaginary part of z, and c and d real and imaginary part of w, respectively, then the way we do operations in this algebraic form, they are simple. You just simply have formulae how to do them. For instance, when you add or subtract, you just do the respective operations with the real and imaginary parts separately. When you multiply, you just sort of do expansion like you did expansion with binomials with real numbers. You just write down these two numbers next to each other and you just expand these things. And when you expand these things, you just remember that I was a special number of the special quality. So it's a number which in square delivers -1. If you keep that in mind, then the expansion, and I'll leave details to you, will be just this one. With the division, it's a bit of a trick. So it's sort of a new thing, something probably you didn't see before. Yeah, so first you just write these two complex numbers in algebraic form, one above the other, but then you do this special thing. You just multiply this fraction, the numerator and denominator, by the number which is the number in the denominator, but you take the opposite to this sign in front of d. So you multiply it by c take d I. So you see the plus in here became minus in here. Technically speaking, you haven't changed much because this fraction is simply identity, so this doesn't change the value of the expression. But now you multiply a numerator with the numerator and denominator with the denominator. And that leads you to, well, in the numerator, you just do the multiplication like you did here, like here. But the denominator is interesting. It turns out and I'll skip the details for you, but it turns out if you multiply these two numbers, the result, if you do the multiplication according to this, the result will no longer have any imaginary part in it. It will be just c squared plus d squared. It's actually, I'll just put it here separately for you. If you have two real numbers, then multiplying a complex number built on this real numbers like this, x plus iy, with the number which is identical but with a negative, it spits out, I'll skip some details, you can easily do that by following this formula. It will just give you sum of the squares of x and y. We'll just see some examples. So I have here two numbers z and y, 2 take 4i and 3 plus I, and we need to find sum. We need to subtract z w from z, we need to multiply, and we need to find the quotient. With the addition, it can't be easy. You just put these two numbers together and you just do the arithmetic right on the spot. For instance, 2 plus 2 plus 2 plus 3 is just 5, and negative 4 and 1 just delivers negative 3, and that's the result. Here, similarly, you just put these two numbers together, but now you put negative in between, and now you say 2 and 3 delivers negative 1, and negative 4 and 1 is just with the extra negative, which is negative 5. Product is my two numbers next to each other. When I expand this, you go 2 times 3 and then plus 4 times 1, so it's 10. It's 10. And the imaginary part will be this negative 4 times this 1, which is negative 4, and this, no, wait a sec, the other way around. This 2 times this 1, which is 2, and this negative negative 4 times this 3, which is negative 12. The result is 11, which is wrong, by the way. Let's just double check. Negative 4 times 3 is negative 12, and 2 times 1, it's 2, so it's negative 10 in fact. Let's just fix this quickly. Negative 10. Now with the quotient, the same story goes. You just put these two numbers together and you multiply it by the number in the denominator with the negative, and then you multiply this across. So you multiply this 2 by this 3, which is 6, and then negative 4. So the first number in denominator here will be 2, then goes imaginary part 14. Let's just double check that. This 4 times this 3 is negative 12, and another negative 2, yeah, that's the one. And in the bottom line, all we have to do, just look down here, we just have to take the sum of the squares of the real and imaginary part of this number here. So we just sum of the 3 square plus 1 square, which is 9 plus 1, which is 10, and that's the result. You can of course split this result in the algebraic form. So in your number, this is the real part of this fraction, and this is the imaginary part of this fraction.